Hello and welcome to Electronics. My name is Fatima Garba Yusuf, and today we are going to explore another part of phase diagrams, which is the lever rule, and we're going to derive the rule first before even implementing it. But first of all, what is the lever rule? Actually, the lever rule tells us about the amount of the different phases in a two-phase region in a percentage weight format. So with the lever rule, we are able to actually calculate the amount or the percentage of the weight of the different we're able to calculate the percentage weight of the different phases that are present in a binary alloy or a binary system. And this is done graphically. For you to understand it, it's actually depicted on a graph by using a tie line, and then the respective weight percentages are calculated using a formula. So we all know that usually when you derive formula, it's easier for you to understand it. So that's why we are going to first derive the lever rule before even attempting some examples based on it. So let's dive right in. And in case you're wondering, a tie line is an isotherm that connects phases in equilibrium. So I'm going to show you a graphical representation of a binary phase system, which is adapted from Callista textbook of material science and engineering. So as you can see here, we have the temperature on the y-axis and the weight percent of nickel on the x-axis. And actually this is from the binary system of copper and nickel. So even though we are shown just the weight percentage of nickel here, we can actually be able to calculate the weight percentage of the copper too from this. Meanwhile, we have two phases here. We have the liquid phase and we have the alpha phase, which is actually the solid phase. And then as you can see, this is actually separated in different colors for better understanding. The green aspect represents the liquid phase, while the blue aspect represents the solid phase. As for the white section, it represents the two-phase region where the liquid and the alpha phase coexist. So when you cool down this solution, or when you cool down the copper nickel phase system, that's when you reduce the temperature. It will affect the percentage of the nickel present, the percentage of the copper present, and of course the percentage of the different phases that are present. So what we're going to do is we're going to try and calculate the actual weight percent of nickel present at this temperature TB given, which is in between 1200 and 1300. So if you have watched our previous video, we did a similar example to this where we had a temperature higher than 1250 will allow the solution to be in the liquid phase completely, and when it is less than about 1150 or so or thereabouts, it's actually in the solid region when the ratio of the original alloy or the ratio being considered is about 35%. So here also, as we mentioned earlier, the tie line is an isotherm, that's line on the same temperature TB. What we mean is that on each point of this straight line here, it has the same temperature. That's why it's called an isotherm. Iso stands for same, so isotherm means same temperature. So it connects these two different phases, the L phase and the alpha phase, and when it's in this two-phase region, you need to calculate the weight percent of the metal we are considering based on what is called the lever rule. And if you look at this straight line, and you also consider this line that is projected vertically upwards from this percentage of 35%, then it might actually strike you as similar to what a lever is, with this point as the pivot. So just like in a lever where you have a weight pressing down and then the effect is projected to the other side, then this is similar to what the lever rule actually is. Meanwhile, don't think that this lever rule is only applicable to just maybe a copper nickel system. It can also be applicable to a system that contains more than two phases, such as this one here. We have the L phase, we have the A plus L phase, we have the A plus B phase, we have the B plus L phase. So here we are just telling you that we have different phases that are coexisting. Maybe the primary phases are the A phase, the B phase, and the L phase. But then in some areas we are having two-phase regions. So this is showing you that even if you have a multi-phase diagram, you can still be able to calculate using the lever rule as far as your isotherm falls in a two-phase region. So now, before we dive into the lever rule derivation, let us first assign values to some of the let us first identify some of the parameters we are going to use in the derivation of the lever rule. For example, let W represent the weight fraction of a phase, and we can use subscripts to distinguish between the phases. For example, if you have the alpha phase, you have the L phase, or you have the S phase, something like that. So in a two-phase diagram with liquid and solid components, it will be maybe easier for you for L to represent liquid and S to represent solid. Hence, you have W subscript S to be the weight fraction of solid component, W subscript L to represent the weight fraction of liquid components. We have C subscript S to represent the composition of a component in solid form. We have C subscript L representing the composition of a component in liquid form. So do not mix these up, because the CS and the CL are actually the values that you are able to determine from the graph. As for the WS and the WL, those are the values that you are trying to calculate. And it is important for you to also note that we can have a particular weight of a particular percentage of nickel in our alloy in the liquid form, and then another percentage of it in the solid form. Likewise, copper. So that's why we have WS, WL, CS, and CL. So if we are having maybe our nickel as our component of interest, then WS multiplied by CS represents the weight fraction of our nickel in the solid form. But for us to understand this more, let us start the derivation in earnest. So we have two unknowns here, the WS and WL, and we'll need two independent equations for us to solve for these two unknowns. So our first equation is going to be based on the fact that our weight percentage of nickel is, or let's say the first percentage of our first component is going to be subdivided into, let's say, if it's a binary system, then its weight percent is going to be divided into the two phases, and when you sum them up, you are bound to end up with 100%. So it simply means that our WS plus our WL is equal to 100%, right? And this is equal to 1. So by saying this, we can take this as our first equation, equation 1. Then our second equation is based on the conservation of mass. Our second equation is based on the conservation of mass, where we have Ws Cs plus Wl Cl is going to be equal to our initial concentration, CO. So this is our second equation. Remember that our values of CO, our value of Cl, and our value of Cs can be found from our graph.